EBN is one of the partners of the TEESAMT project, and we have been supporting the organization of the webinar series. The TEESAMT project has been organizing a series of webinars with the service providers by presenting the validated characterization techniques and some user cases. And for the last webinar today, we have the pleasure to host the expert Marius Flugel from the Center of Solar Energy and Hydrogen Research from Germany. He will be presenting a session on GD-OES depth profiling and in situ optical microscopy for deep insight onto lithium batteries. Marius will be leading the main session of the webinar, and if you have any comments or questions during his presentation, please feel free to share them in the chat box, because we will have a Q&A session right before the end of the webinar. Just before we get started, I would like to give the floor to our project coordinator, Fabien Perdoux from CEA, and he will give us some background information about the TEESAMT project. Fabien, the floor is yours.
Thank you very much, Agatha. So TEESAMT project is an open innovation test bed for electrochemical storage materials. So if you can, yeah, thank you. It's based on the idea that the European battery market is growing very fast at an incredible 25% per year. And so the development of a competitive battery value chain in Europe is, of course, a top priority. And this development must rely necessarily on understanding and this characterization of the various processes that happen in batteries, which are very complex. And in fact, we have in the European research labs a variety of advanced characterization techniques which exist, but which are underused by the companies often. So the project TEESAMT aims to provide an easier access to these advanced characterization techniques and services to the companies in the domain of electrochemical energy storage materials. And so this is done in 3 steps. The first one was to set up the platform, the Open Innovation Testbed. The second one, to demonstrate the added value by solving some problems which are brought by our service users, and to ensure the growth of the platform, its longevity, including after the end of the European project. The project gathers mainly two kinds of partners. Some of them are service providers, providing the characterization techniques with a variety of techniques and chemistry, morphology, structure, performance, modeling, and so on. And the other ones are service users, so they are industrials bringing their question, their samples, their user cases to test the platform, in fact. And we have 2 specific partners, CERMA with the single entry point, so making the link between the providers and the users, and CEA has a specific role as coordinator, of course, but also as dealing with a database in which we store all the information and the samples, the tests, and the results to build a higher degree of expertise. A very quick view on the timeline. In fact, today is rather the end of the project, because the end is in August 2022. So the setting up of the organization is finished. The test phase is, we are in the end of the test phase. We have gathered external partners as users and as providers, and we are nearly ready now to end this European project and to begin the commercial activity. So to provide these characterization services as a paid offer. And so now I will leave the floor to Marius.
Thank you very much. Thank you for the kind introduction and for the introduction of the TEESAMT project. My name is Marius Flügel and I'm a PhD student at ZSW, the Center for Solar Energy and Hydrogen Research in Baden-Württemberg. The ZSW was founded in 1988 as a non-profit foundation, and in 2021 it already has 300 employees. Our goal is the industry-oriented research and the technology transfer in the field of renewable energies that you can see in the figure below. So in Ulm, we are mainly active in batteries and fuel cells, but we're also active in regenerative fuels like power to gas and in wind energy. Our locations are Ulm, where we are with 2 locations, the main building that you can see on the right top picture and the E-Lab, and we also in Stuttgart and Witterstahl with the solar test facility. In the battery research, we are experts at materials research in the field of lithium-ion batteries, as well as post-lithium-ion batteries, and also post-mortem analysis. We have expertise in the electrode and cell manufacturing from the small-scale coin cells, pouch cells, and also cylindrical and PHEV cells. The webinar today will be about GD-OES and in situ optical microscopy. And for both cases, I will present user cases and application. So, GD-OES is short for Glow Discharge Optical Emission Spectroscopy. It's a spectroscopic method which allows the quantitative and qualitative analysis of metallic and also non-metallic solid materials. Our sample that we want to investigate is put into electrical contact with our GD-OES cathode. It's placed right under the GD-OES anode, which can be seen here as half circle. And this is just a cross section. The real GD-OES anode is completely round. And the plasma chamber is sealed by the sealing ring. The plasma chamber is then evacuated and filled with argon gas. After that, a high voltage of 500 to 1000 volt is applied between the anode and the sample. Those are not in contact, so by the high voltage, electrons from the sample surface are accelerated towards the anode, and due to their high speed, they ionize argon atoms during the collisions. The argon atoms are then accelerated towards the sample surface to do a positive charge, and when they hit the sample surface, they sputter off sample atoms. Those sample atoms then diffuse into the plasma, where they collide with argon atoms and electrons, and are electronically excited during the collision. During de-excitation, they emit light with a specific wavelength, which is then focused onto a concave grating and split into its individual components, which is then detected by photomultiplier tubes or a CCD camera. For our non-metallic samples, so our graphitic electrodes, we are applying a radio frequency voltage, so that the voltage is positive for a small part of the cycle. This prevents the buildup of a charge on the sample surface. And this RF mode also has the advantage that the ionization is much more efficient than in DC voltage. This allows lower voltages for our RF mode, and sensitive samples, like samples with heavy SEI formation, can also be measured without sample damage. For most of our samples, we assume a linear relationship between the emission intensity of the element and the concentration of the element in the sample. However, in most cases, especially for our graphitic electrodes, the removal rate and the emission yield is dependent on the matrix. To compensate for small changes in the composition of the electrode, we put our emission intensity of the element in reference to a reference element, which in our case is argon. Argon as discharge gas is very much abundant. For the calibration, we use artificial used electrodes. Those are electrodes that are prepared in the same way as real electrodes, but we add additives like silicon oxide, copper oxide, or lithium dihydrogen phosphate to introduce elements like silicon, lithium, or copper, which are not present in fresh electrodes. By comparison with, for example, EDX, we can see that with GD-OES, we can quite nicely quantify all elements. Why do we need a depth profiling method like GD-OES? For most methods, it's not possible to create depth profiles of our samples and also to quantify, for example, lithium. There are some techniques, for example, XPS sputtering, but the sputtering rate of this technique is very low. And with GD-OES, we can sputter through a whole electrode within a few hours. To show you the aging effect, we aged several cells until a different state of health. After the aging was over, the cell were completely discharged and then opened, and the electrode were given to ICP analysis. We saw a correlation with the aging degree and the amount of lithium, phosphorus, and manganese in the negative electrode in the anode. The lithium increase is due to the trapping of lithium in the SCI during prolonged aging. This phosphorus originates from the conductive added salt, the LiPF6, which is decomposed during the cycling, and manganese dissolved from the cathode surface and migrated to the anode. With GD-OES, we could observe that lithium was mostly found at the anode surface, where there's a heavy SEI formation, which could also be observed with a light microscopy of the cross-section here. For state-of-the-art anodes, silicon is added as material with a high specific energy, high specific capacity, and therefore we also investigated the aging processes of silicon graphite composites. And those cells were aged at room temperature for 700 cycles until it reached 80% of SOH. And the capacity loss within the first 100 cycles was close to the capacity loss within the next 600 cycles. However, we did not see a sudden capacity drop, so the aging mechanism doesn't change over the cycling. We observed a double layer film formation. So there is a classical carbonate-based SEI, which is present in graphite anodes, but also a lithium silicate-based film, which forms during cycling. The silicon film at the surface gets broader with prolonged cycling, and this can also be seen in the cross-section. Here around the silicon particles, we see the SEI film, or the film around the silicon particles, but there is a sharp border between the silicon particle and its film. After cycling for 700 cycles, the boundary between those particles and the film will get more and more diffuse. Our main focus with GD-OES is on the detection of the lithium deposition on anodes. This is very relevant as lithium plating on top of the anode poses a serious threat to the electrode. It's possible for the lithium to reintercalate into the anode or to dissolve during discharge. However, some of the lithium may not have contact to the anode anymore and is therefore so-called dead lithium, which can react with the electrolyte and form SEI components, which are then blocking the pores. This leads to an increase of the internal resistance and a decrease of the Coulombic efficiency and the capacity of the cell. The energy and the energy efficiency also decrease. The reaction with the electrolyte is very exothermic. This can lead to gas formation, venting, or in the worst case, even to fire and rupture of the cell. The aging is visible on the microscopic level. On the left, you can see a fresh cell. With SEM, you can see the pristine surface, and one can distinguish the individual particles. With the GD-OES depth profiling, we see a normal depth profile. We see lithium to a normal degree and also phosphorus. After aging at low temperature, which leads to lithium deposition on top of the anode, we see a film which covers completely the surface, and we cannot see the graphite particles any longer. At higher magnification, we can see the dendritic lithium, and with GD-OES depth profiling, we found that the lithium deposition was only happening on top of the anode. After cycling at high temperatures, which leads to a heavy SEI formation, we still can see the graphite particles. However, due to the SEI film, the smaller particles are not distinguishable anymore. And with GD-OES depth profiling, we see an increased amount of lithium in the anode. We can even see different aging mechanisms on top of one electrode. Here you can see in the photograph of such an electrode, the blue area exhibits strong SEI formation, whereas the golden area shows lithium plating on top of the anode. This can also be verified with SEM images. Recently, we've developed a technique to quantify the minimum amount of lithium plating on top of the surface of the anode. For this, we assumed that lithium in the SEI is only present as lithium oxide. Why lithium oxide? Lithium oxide has the highest amount of, or the highest percentage of lithium of all SEI species. To calculate the maximum amount of lithium oxide in the anode, we use the detected amount of oxygen, and any lithium that is present and not bound as lithium oxide has to be metallic lithium. For silicon-containing cells, this assumption is not so easy because silicon oxide also contains oxygen, and we have to subtract the amount of oxygen bound in silicon oxide before subtracting the amount of oxygen bound in bound in lithium oxide. However, we do not know the exact amount of oxygen in silicon oxide, therefore we can only give a corridor in which the minimum amount of lithium plating is located. To give you an example how we use GD-OES in together with different complementary methods, I'm going to present you our recent research. For this, we bought 3 18650 cells, which all contained silicon in the anode. Those cells were then aged at 45 degrees Celsius until the SOH was 80%. So we lost 20% of capacity, either by lithium consumption or by loss of active material. The aged cell, as well as the fresh cells, were opened in the glove box, and the anode were then used to build coin cells. Those coin cells were then used to get the anode potential. Here in the lower right, you can see a graphite electrode and the silicon graphite electrode. The graphite is mainly electrochemically active below a potential of 0.2 volts versus lithium, whereas the silicon is electrochemically active between a potential of 0.2 and 1 volts. Knowing this, we can see that for cell type A, we saw the 10% capacity loss, which was mainly caused by the loss of active material, mostly the loss of active silicon. However, we lost 20% of capacity. So for cell type A, we saw capacity loss caused by loss of lithium inventory as well as loss of active material. For cell type B, we hardly saw any capacity loss from the active material, only 5%. So the main capacity loss has to be due to loss of active lithium. For cell type C, we saw that lithium was hardly active anymore. So most of the capacity loss was due to loss of active material. With SEM, we got similar results. The fresh cells can be seen in the left column. And after aging, we saw heavy film formation around the silicon particles for cell type A and cell type C. For those particles, the lithium has to diffuse through a more than 1 micrometer of film to get to the silicon. For cell type B, where we didn't see any loss of active material, there is here's very small film around the silicon particles. The GD-OES depth profiles of the fresh cells revealed also that all those cells contain silicon, and we saw a low amount of lithium in the anodes. After aging at 45 degrees Celsius, we didn't see any lithium plating, but we saw an increase of the amount of lithium in the anodes. For cell type A and B, we saw a high amount of lithium, which was due to the loss of lithium inventory, which was obviously trapped in the anode. For the cell type C, we didn't see a sharp increase of lithium in the anode, which is also conclusive with the fact that we observed loss of active material. However, if we cycle them at low temperatures, 0 volts for 0 degrees for cell type B and C, and minus 20 degrees Celsius for cell type A, we saw lithium plating, which could be quantified with our recently developed method. What we did then was we took a separate set of cells, first cycled them at 45 degrees Celsius until we reached an SOH of 80%, and then we cycled them at 0 degrees or minus 20 degrees. So we combined both aging procedures and wanted to know if lithium plating is still possible. It's still possible for cell type C, where we saw a loss of active material, but the lithium inventory is still there, so lithium plating is still possible. However, for cell type A and B, where we saw a decrease of cyclable lithium plating did not occur after aging at low temperatures, probably due to the loss of lithium, which can be deposited on the anode surface. Our method can also be used to investigate copper dissolution and redeposition after over-discharge. For this procedure, for this experiment, we also used 18650 cells, which were over-discharged to 0 volts for a different amount of time. So 100, 290, 430, and 1000 hours. And also a second set of cells was used, which was simultaneously to our previous experiment, was first aged, however, this time at low temperatures, and then over discharge to 0 volts. We used ICP to investigate the lithium and the copper in the anode and the cathode. For the lithium amount in the anode, we saw the decrease of the lithium after over discharge, which was probably due to the SEI decomposition due to the high anode potentials, and then the migration of the lithium to the cathode. And we also saw a sharp increase in the copper amount in the anode, which can be seen here, and also increase of the amount of copper in the cathode, which then probably migrated from the anode to the cathode. The highest amount of copper was found for the previously aged cells. SEM images showed that the pristine electrode, the fresh one which was not over discharged, showed graphite particles, but no additional compounds. For the cell that was over discharged without previous aging, we saw a compound which was located between the graphite particles, and EDX confirmed that it contained copper. For the cell that was previously aged at 0 degrees and then over discharge, we saw a much higher amount of copper, which was this time located on top of the graphite particles. The cross-section of those cells revealed that the copper was originated from the copper current collector, obviously, and the copper current collector showed signs of pitting corrosion instead of homogeneously dissolving. And the holes of the current collector of the previously aged cell were much larger, which is agreement to the ICP results. EDX mappings of those cross sections showed that the main amount of copper is redepositing at the anode surface. However, it's not possible to quantify the amount of copper with EDX. So to get a depth profile, we have to use GD-OES. And with GD-OES, we also saw a high amount of copper, which was indeed deposited at the anode surface. For the fresh cells, we did not see any copper at all, which was expected. And in conclusive to the ICP results, we saw the highest amount of copper for the previously aged cells. So to summarize our results with GD-OES, we saw that for all our cases, we saw a surface enrichment. For lithium plating, we saw that lithium was depositing on the surface, anode surface, and also the SEI film mainly formed at the anode surface instead of a homogeneous distribution in the electrode. We also saw the silicon film which was forming was mainly forming at the anode surface. And copper which was dissolved during over discharge, we deposited also at the anode surface. So we got those results, and those results are consistent with complementary methods and simulations. So we are very sure that the results we generated with GD-OES are as they are. Now I want to present you the in situ optical microscopy, which is operated by my colleague Christine Hochgräfe. The in situ optical microscope, which we use at ZSW, allows for the direct observation of lithium-ion full cells in the cross-section and with the simultaneous recording of the electrochemical data. With the color change of the graphite anode, we can observe several processes in the electrode and also on particle level. And those are the speed of the lithiation front of the LEC6 and LEC12 phase. We can also use the in situ optical microscope to observe the electrode expansion during cycling, and we also observed particle reconnection and deconnecting during cycling. By observing the color change of single graphite particles, we can also estimate the apparent diffusion coefficient in graphite particles. There are several setups that can be used for in situ optical microscopy, like top view or side view. However, we settled for the cross-section setup. In the cross-section setup, two 12 diameter positive and negative electrode and two 18 micrometer cell guard separator are used as electrode stack. A homogeneous pressure of is applied on the electrode stack by steel blocks and springs of both sides of the stack. With a knife, the cross-section is then prepared, and the cross-section is dried under vacuum conditions for 16 hours at 80 degrees Celsius, after which the cell is then filled with 150 microliter of electrolyte, also inside the glove box. The stack is then sealed, and all openings additionally sealed with Kapton foil to prevent any intrusion of humidity or atmospheric gases. The in situ optical microscope is placed in a dry chamber with a dew point lower than -45 degrees Celsius to lower the risk of water intrusion into the stack. We saw a difference in the color change between charge and discharge. During charging, we saw that the red LEC12 phase was already appearing at an SOC of 30%, and the golden LEC6 phase was appearing at an SOC of 70%. However, during discharge, the golden phase is hardly visible anymore at an SOC of 90%, and the red LEC12 phase vanishes at an SOC of 60%. With in situ optical microscope, we can only, unfortunately, observe the surface of the particle. However, the particles are first lithiated from the surface and delithiated also from the surface. So during charge, there is a higher degree of lithiation at the outer part of the particles than it is inside the particles. And during delithiation, the particles seem more delithiated than they actually are. However, by comparison with the volume expansion, we can be sure that, for example, here at an SOC of 30%, the cell is not completely discharged yet. Here you can see a video of the cycling of the cell in the cross-section. And we saw that the anode expands, the anode expansion is between 4 to 12%. So the maximum expansion is 12%, and the irreversible expansion is 4%. This correlates with the reports of the literature where the anode expansion is 4 to 13%, which was found with telemetry and XRD. The cathode expansion is only 1 to 2%. It does not correlate with the potential, so the cathode and separator expansion can be neglected. For the estimation of the solid diffusion coefficient, one has to keep in mind that graphite particles consist of several grains with various orientation. One of those grains is marked here with the black outline, and by the color change during the 3L to phase 2 transition, we were able to estimate the solid state diffusion coefficient. The color slowly changes from blue to red, and the area, which was the area of the respective phase, was judged, was measured by judging the color by eye. And the area is then plotted against time using this formula. The slope of those curves is then the apparent diffusion coefficient, which is in the order of 10 to the power of minus 10 square centimeter per second, which is in the same order of magnitude as literature results. During the last discharge, this particle, which is marked here, lost contact with the electrode. So still the red LEC12 phase. And during the next charge, you can see that the surrounding of the particle changed the color from gray to blue to red. And those points that are marked here are also marked on the potential curve. After T6, the particle also changes color until it's completely charged at T9. During discharge, the particle is also deviated only until time point 11, after which the color of this particle does not change anymore, whereas the surrounding of the particle is further deviated. While looking at the electrode expansion, we saw that the reconnecting and deconnecting of this particle happens between an electrode expansion of 8 to 9%. And last but not least, I want to present you a user case in cooperation with FARM, where we were asked what electrode combination works best. We had two anodes, a thick one and a thin one, which had the same areal capacity, only a different density, and also a thick and a thin cathode, which also had the same areal capacity, again with a different density. And during cycling, the first charge cycle was at 0.1 C, charging with CC/CV, and discharge also at 0.1 C. The second charge was with 1 C. And we wanted to see if there's a lithiation gradient in the anode. And during the 0.1 C charge, we can see a homogeneous color change from gray to blue to red and finally golden. And during the 1 C charge, you will observe inhomogeneous lithiation. As you can see, the lithiation spread from the anode surface to the copper current collector. The electrochemistry is aligned with coin cells, and we saw a high agreement. Now the combination with the thin electrodes. Here we saw again homogeneous charge, change of color during the 0.1 C charge, and the lithiation gradient during the high C rate of 1 C. Okay, now let me summarize those results. With in situ optical microscopy, we saw a color hysteresis between charge and discharge, which was caused by inhomogeneous lithiation of the graphite particles. We were able to estimate the apparent diffusion coefficient, which is in the order of 10 to the power of minus 10 square centimeter per second for both the transition of 3L to 2 and also the transition from the LEC12 phase to the LE66 phase. We saw a lithiation gradient at high charging rates, and we saw that the anode is mainly contributing to the cell expansion with expansion of 4 to 12% for graphite anode, and hardly any expansion of the cathode. For the farm user case, we saw no significant differences between both electrode combinations. To conclude the webinar, with glow discharge optical emission spectroscopy, we were able to investigate the aging mechanism of lithium-ion batteries. We are able to record elemental depth profiles, also including lithium and copper. And we get those depth profiles from the surface to the copper current collector within a few hours. And those results are consistent with complementary methods. With cross-sectional in situ optical microscope, we can simultaneously record the lithiation and dilithiation and the electrochemical data. Those results are reproducible and comparable with coin cells, and we can investigate different cell chemistry. Our next project is the investigation of silicon-containing anodes. I want to thank the TEESAMT project and the European Commission, which granted this project, and also our project partners. And with this, I say thank you for your attention. And if there are any questions, please ask them.
Thank you very much, Marius, for your presentation. It was very, very interesting. And as you just said, maybe we can open the floor for questions. Yeah, I already see Jakub from the SRF has his hand raised. Please feel free to unmute yourself and jump in.
Okay, thanks. Thanks, Marius, for a nice talk. So can you compare those techniques you show? That means the GD-OES, the SEM and EDX, and the optical techniques. Like, what are the really advantages, disadvantages, and complementarity between those techniques?
Yeah, it's for SEM and the comparison of SEM, EDX, and GD-OES. The GD-OES has the advantage that we can observe lithium, which we cannot with EDX. And therefore, we use those combinations very often together in comparison. But with EDX, for example, we can observe our cross-section and see different elements, and we can make reasonable quantifications. However, for GD-OES, we always need a calibration to quantify our elements, and the detection limit with GD-OES is much higher or lower, if you will, than EDX. So EDX is, in my opinion, more sensitive. And with the in situ optical microscopy, we can see the different lithiation degree in the anode by judging the color. However, as we mentioned, we have to keep in mind that we only can observe the surface of the particles. So there is this color hysteresis, which makes it hard to reliably give the exact SOC of the cell without the electrochemical data.
Okay, thanks.
Okay, any other questions? Please feel free to unmute yourself. I'm having a look at the chat. I don't see any questions at the moment. Just in case, if you will have also some questions later, I'm sure we can share these with Marius, and he will be happy to reply.
Yeah.
Yeah. So I guess we can slowly come to an end of this webinar and also the whole series. Today it was the last appointment we had with the TEESAMT webinar series, and we started around a year ago, and we had in total 8 webinars, and we presented 9 characterization techniques and user cases. It was a great success, and just for you to know, all the recordings have been kept, and they are most of them already published on the website. We're just waiting for the approval of the last 2 webinars. So if you miss some of them, maybe you wanna watch it back, you can go on the TEESAMT website. I'm gonna share the link to the website in the chat, and also I would like to remind you all that the project is coming to an end, and we will have one final event which will take place in Grenoble next month. It will be on the 5th of July. And I'm gonna also share in the chat box the link to the registration and to the page event. So feel free to join us. And thank you, Marius, for your presentation today. It has been very nice having you. And thank you also to all the service providers who have been presented all the characterization techniques. And of course, a big thank you to all the TEESAMT partners that have been supporting these activities. And of course, thank you to the European Commission for granting this project. I guess we can close the session. Thank you, everyone, and have a nice afternoon. Bye.